Hi, everyone. So today we're going to look at the complex exponential function and the way that we can understand some of the basic ideas of complex analysis by thinking about how we define the exponential function, how we extend it to values it doesn't initially take, and what sort of behavior it reflects about functions evaluated on complex numbers. So the key idea in thinking about the complex exponential is the extension theorem. So remember, the extension theorem is basically the assertion that theorems and properties that hold for functions with power series of real calculus also continue to hold those properties in complex analysis or functions with complex entries instead. So let's start by looking at maybe the most important function of calculus, which is the exponential. So the natural exponential e to the x. So in real variables, at some point through one definition or another, you stumble across the power series definition of e to the x, which looks like the following: x to the n over n factorial. And one thing that we should note is that the radius of convergence of this thing is infinite. That is to say that the geometric term x to the n is dominated by the factorial term in the denominator of the fraction. So this series actually converges no matter what value of x you plug in, which makes e to the x a well-defined function. And then in real calculus, you also end up noting that the the natural exponential function can therefore have derivatives taken, and you get the same formula out as you put in, which means that the derivatives are also e to the x. And so it preserves its convergence properties as you continue. So one thing you may not have thought about when you saw this in the past in calculus is that the identities of exponentiation induce certain identities on power series. So an interesting one is the idea that if you think about what the power series for e to the a plus b must be, then you can split that up, or you can evaluate that in the power series by just taking the a plus b and plugging it in place of x, right? That's exactly what it means to evaluate a function e to the x at a particular x as you plug it into the power series. But the fact that e to the a plus b is e to the a times e to the b induces this identity on the power series. So it must be the case that the product of the power series is equal to the original power series evaluated at the a plus b variable. So we end up with this strange factoring formula, which to me anyway is not at all obvious that should be true, except that the power series actually forces it to be true. And what's going to happen is the extension theorem is going to say that because that identity held for real variables, then it's also going to hold for complex variables as well. And you get some interesting consequences out of that. The first of which is that if you think about z as x plus iy, then we get the decomposition e to the z is e to the x times cosine x plus I times the sine of y. And this is a familiar argument if you've worked with power series in the past, but this actually kind of is where the deep connection between cosine, sine, and natural exponential come from. And indeed, why cosine and sine are infinitely differentiable in some sense. So with those sort of patterns, I mean, obviously anything with a power series is infinitely differentiable, but cosine and sine have this repeating pattern where they turn back into themselves. And that's very much related to the same behavior of e to the x. The way that you show this is you use the identity that we just asserted must hold for complex numbers by the extension theorem. So you write e to the z is e to the x plus iy, which splits into e to the x, e to the iy. And now I'm not going to evaluate e to the x in a power series, but I am going to evaluate e to the iy. So I'm going to take e to the x and leave it alone. E to the iy, I can view as the evaluated power series iy to the n over n factorial. And if you think about that for a minute, we can use the fact that we know a pattern of how I evaluates. I is itself, I to the second is -1, I to the third is -I to the fourth is +1, and then the pattern repeats. I to the fifth turns out to be equal to I, and so on, because I to the fourth is 1. And so what that means is that we can decompose this series into two pieces. Pieces for which the I disappears when we take the power. So every even power will give us I squared, y squared, which is minus y squared, or I to the fourth, y to the fourth, which will be positive y to the fourth. So all of the even terms, the I disappears completely. In the odd terms, there'll be an I left over, but the signs will alternate. And so what you end up with is this. This turns into e to the x times one series where of all of the even terms of the power series, and that's going to be minus 1 to the n. The alternation comes from the fact that these alternate. So in particular, I squared and I to the fourth will alternate as I to the sixth, I to the eighth, I to the 10th, and so on, follows the same pattern. We only had even exponents, so we write y to the 2n, and then we divide by 2n factorial. So that's part of the original series. If we evaluate the odd, so what's left over is the odd terms. Well, the odd terms have the same sort of structure, except now there's going to be this extra I left over in each term because I to the third is minus I, and I to the fifth is I. So this turns out to be equal to I times the sum from n equals 0 to infinity of another alternating pattern, minus 1 to the n, but now the exponents are all the odd exponents. So we get y to the 2n plus 1 over 2n plus 1 factorial. And it shouldn't be surprising to you that those are power series that we recognize. In fact, power series that are entire in the sense that they have infinite radius of convergence. And those particular power series, which we derive using Taylor's formula in real variables in calculus, this is cosine of y plus I times the sine of y. And those of you that have seen this in certain contexts may have actually also seen this as e to the x times something called cis y, or cosine I sine. So this is sort of more common in high school than college, but you may recognize it in that form. And this is a profoundly important observation because essentially what it says is that the complex exponential function is doing something where one part of it, the real part, the e to the x part, you can think of as the radius of a complex number, because this part, this cosine of y plus I sine y, if you interpret it on the unit circle, if you interpret complex numbers as the real part and the imaginary part, sort of like R2, this implies that e to the iy is a number on the complex unit circle. So if we drew that really fast, this is essentially saying we can think about this as a radius, and this as a unit circle number. So that's a really, really important observation. And in the case where the number is purely imaginary, then we get what's called Euler's identity. So this is a very important identity. Essentially says that e to the it is equal to cosine t plus I sine t. And the picture that you should carry around in your head for this is you have what's called the complex unit circle, normally denoted t, sort of in this fancy double stick t. And so this is the unit circle. And that e to the it is just a point on this circle. So here's e to the it. And the x coordinate or real coordinate of e to the it is the cosine of t. And the y component is the sine of t. And that gives us that way of stepping back and forth from the sort of two real dimensional version of the complex numbers with the complex exponential. If we think about e to the it as a function and we let t go from 0 to say 2 pi, then what we're going to get is a function that basically just rotates around the circle. So thinking of f of t as just e to the it, and if we let t, say, increase from 0 to 2 pi, well, you can think about what that complex function is doing is it starts at the point 1, 0 in the unit circle, and then flips around all the way and comes around back to the beginning point again. So this is very closely related to polar functions that we learn in calculus. And in fact, that's an important observation to make, is that this identity lets us perform what's called the polar decomposition of a complex number, which is very useful for a lot of calculations, particularly calculations involving exponentiation. So the polar decomposition of a complex number, we can always write z is equal to re to the it, where r is the modulus of z, and then e to the it is the sort of angular piece. So how we rotate around to the circle to give us a vector that we can follow to get the complex number that we're interested in. So again, the picture here that you can think is if you have a z, then you can think about locating an angle t, which gives you a point on the unit circle that tells you where to go to get to the complex number, and then some radius that you travel out to, so that this radius right here is the length of z. And again, that picture should make sense because it's just the standard right triangle picture that we use all over the place. Okay. Now, by convention, we have to fix a certain set of angles. Maybe you've seen this before when we're studying things like the inverse functions, inverse trigonometric functions. In order to make those well-defined, we have to fix a set of angles to make those functions have inverses, because they're not intrinsically one-to-one. And so the problem is that there's lots of angles that represent the same complex number. Once you have any angle that represents a complex number, any multiple of 2 pi added to that angle will also represent the same number. So normally, because we're going to want to work with inverses of functions, that's partly what we're driving to here, is that we want to talk about logarithms. We need to come up with some way of making sure that complex numbers have unique angles that determine them. And so we pick something called the principal range of angles, which looks like this. So it's the set of angles from minus pi to pi. And the picture there, which is related to the picture, say, for the inverse of the sine from calculus, is that we are choosing our angles in the following way. So from minus pi to pi means that we're starting here on the minus pi. This is the angle 0 by sort of convention, the same as in calculus, right? So the positive real axis is the 0 radians. We start here at minus pi, and we come around the circle until we come back to pi. And the actual imaginary line itself, the negative, or sorry, the negative real axis, we approach that from the top, that is from the pi side, but not from the minus pi side. So we notice here we've got a strict inequality. And the fact that we have this jump where we can go from where angles can jump up, right? As we wrap back around again, we end up going from the same angles if we compute their sine and cosine, but the angles themselves differ by 2 pi. That's going to turn out to be really important in analyzing how complex functions behave. So those polar angles are so important that they have a function associated with them called the argument, which eats a complex number and spits out the angle that determines it. And the principal argument function, and I'm using the word principal here to connect with this idea of the principal range, is the argument function that tells you what the polar angle is for a complex number restricted to the set of angles from minus pi to pi. So every complex number will have a unique argument between minus pi and pi. And the function that produces that thing is called the principal argument. And we know we're working with a principal argument because we use the capital A. So arg with a capital A always means it's going to spit out values between minus pi and pi. If you want some examples here, you can think, what is let's let z be equal to root 2 plus I root 2. So perfectly legitimate complex number, carefully chosen so that I can write it in the form 2 times root 2 over 2 plus I root 2 over 2. This is a unimodular number, so that is it's a number that's on the unit circle, because it's easy for me to pick out the angle. So this number in polar form is going to be 2e to the I pi over 4. Because remember, that's 2 cosine of pi over 4 plus I times the sine of pi over 4. And that there are many angles that we could have chosen to go here. The reason I picked pi over 4 is because pi over 4 is the angle that's between pi, and minus pi. And so the principal argument of z is going to be pi over 4. It tells you what the angle is that produces that in that range. Okay, so that's kind of a short video covering the basics of polar decompositions, the relationship of complex exponentials to the argument, the idea that complex numbers have this e to the it, which is this incredibly important function that really is telling you something about the way that a function is rotating. So a big theme that comes up in applications, both in science and higher mathematics, is that complex numbers encode a rotational component. So the reason they're used in things like the study of signals or the study of Fourier series, any sort of Fourier decomposition, has to do with the fact that e to the it embeds all of that cosine plus sine behavior that represents rotating around a circle with a certain set of frequencies. So complex exponentials can be used to pick up information about frequencies of even real variable, or functions of real variables, real coefficients. All right, so I'm going to stop this particular video. The next one, we're going to talk about how we can use these ideas, the argument and the polar decomposition, to recover what a complex function looks like. Recover what the inverse of a complex function looks like, including the most important inverse, which is the logarithm, which is the inverse of the complex exponential. All right, so I'll see you next time.